Hey guys, Mr. Hire here. We're going to take a look at Chapter 6, Section 4, the last section before our next quiz. And we're going to prove triangles are similar by SSS and SAS. So yesterday we learned that we could prove two triangles are two triangles are similar by using AA. So if we could show that two angles of one triangle are congruent to two angles of another triangle, then we could show that they are similar. When we first started this, to show that two triangles were similar, we needed to know that all of their angles were congruent and all of their sides were proportional. So like A to B, A to B, A to B, which if we matched up the corresponding sides would just be AB over AB over AB, just meaning that they make the exact same fraction every single time. So I could have used whatever numbers I wanted there, but they had to equal the same exact fraction each time when reduced. So what we're looking at here is that we're proving that two things are similar, and when two things are similar, it means all of their sides, the corresponding sides, are proportional, and all of their angles are congruent. So what we're going to add on today is that we can also use SSS and SAS to prove that two triangles are similar. So that's what we're going to do in today's slides. Okay, so the first one we're going to look at is the SSS similarity theorem. Obviously SSS is side, side, side. And it says if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So not only can we just look at two of the angles to see that two triangles are proportional, we can also look at all three sides of each triangle and compare it to all three sides of the other triangle. And if their corresponding parts are proportional, then what we've So we've got AC here on the left of the big triangle and DF on the left of the small triangle. We've got CB, the bottom of the big, FE, bottom of big, AB, the right-hand side of the big, and DE, the right-hand side of the small. So I'm just going to match those up there, and I'm going to match them up so their corresponding parts match up, meaning I'm going to match AC on the left with DF on the right. We can also match up AB with DE, and then finally we'll match up CB with FE. So notice that everything over here was from the left-hand triangle. I put all the left on top. I'm putting all the right on bottom. And I just did that because they didn't tell me how to compare them. They didn't say compare ABC to DEF. So I just had to put one of them on top and one of them on bottom. And I had to continue doing it that way. So now I'm going to start matching those up. AC is 10, DF is 5. AB is 8, and DE is 4. We've got BC is 6, and FE is 3. So we've got those three fractions set up. We just need to verify that they are all three proportional, that they all have the exact same measurement when reduced. So we get 10 over 5 when we reduce that, we get 2 over 1. 8 over 4 is 2 over 1. 6 over 3 is 2 over 1. So in fact, all three sides of this triangle are proportional. So what we can say is that this triangle ABC is similar to triangle DEF. And we knew that because we compared all three sides and they worked out to be the exact same fraction when reduced. If any one of those three fractions had been something different, then I could not say they were similar. So that's what we're looking at, comparing all three sides of one triangle with all three sides of another triangle and verifying that they're proportional. Okay, so for SAS similarity theorem, we can now use AA, we can use SSS, and now we're adding on SAS as ways of proving that two triangles are similar. So it says if an angle of one triangle is congruent to an angle of a second triangle, we can see that they've marked an angle as congruent to another angle. And the lengths of the sides including these angles, so it's an included angle, meaning that the side on the left and the side on the right of that angle need to be proportional. So we're going to check them proportional. So we can tell the angle is congruent, but now we need to check the sides that are proportional. So you go, well, how do I know which one to compare to which? So like I've got 10 and 8 and 5 and 4. We can't just mix them up however we want and say, oh, we kind of made them proportional. So if you look at it over here on the left-hand side, I've got the larger number and the smaller number. And I'm going to do the same thing over here. I've got the larger number and the smaller number. Because 5 is larger than 4, so large and small, and 10 is larger than 8, large and small. So really the long side, if they're going to be proportional, will match up with the long side and the small side with the small side. So what I'm going to do is I'm going to check those to see if they are proportional. I'm going to do AC over DF, and I'm going to check to see if that's proportional with AB over DE. So AC is 10, DF is 5, we've got AB is 8, and DE is 4. So we get 2 over 1 equal to 2 over 1, and we have that included angle, so we don't need that third side there. So in fact, ABC similar to DEF in this one. Okay, so here is a quick summary of our 3 postulates. We've got the AA similarity postulates, where you have to prove that 2 angles of one triangle are congruent to 2 angles of another triangle. If you can make those 2 match, then we can say that these are definitely similar. So that is one of 3 new sets of rules that we can use to prove that these triangles are congruent. And when you match them up, just think about the angles. So like here, like they're making the statement that A is congruent to D, B is congruent to E. So ABC here is ABC. Notice I started at the double lined angle, went down to the single line. I'm going to do the same thing here. Double line down to single line, so DEF, they're similar. Because you might have to construct similarity statements. The second was SSS, and we need to verify that all 3 sides are proportional. So we compare the corresponding sides, rather, that we need to compare all 3 corresponding sides and that they're all proportional. Again, meaning that they make the same fraction. Check all 3 sets. You can't just assume that they are unless somebody tells you they're already similar. Well, then you know those sides would be proportional. Last but not least, the SAS similarity theorem. So here we've got a congruent angle. So we would check AB against DE, and we would check AC against DF, and if those sides are proportional, those 2 sides, the ones that have the included angle there, remember when we have included, it's like it's pinching the angle there. Since we've got that included angle, if those 2 sets of sides are proportional, well then we've got similarity. Okay, this is one that I think is one of the harder ones, so you may have to go back and watch this one a little bit. We've got if triangle XYQ is similar to XZP, they're telling us that it is similar. They're saying, does it follow that triangle XPQ is similar to XZY? So based on the first one, if the first thing is true, does it make it true that the second is true? So we're going to take a look at this information here. So XYQ, that triangle is right here. XYQ, right there. And the other triangle XZP is right here. XZP. Those 2 triangles there are the triangles that they are saying are similar. Well, one of the things I noticed is that they have the same angle, like right up there. Like one thing that's common about those 2 triangles is they have that exact same angle right there. And it says right there, it says that angle X is congruent to angle X, like we know that right there. But it also tells us some things about the sides. For example, by looking up here, I can see that side XY and XZ are the same thing. So they're not the same thing. They are proportional to each other. They're the sides that match up. So those 2 corresponding sides match up, and I just looked at the similarity statement to get that. I also know that YQ matches up with ZP, so YQ matches up with ZP, and the other combination XQ matches up with XP. XQ, XP. I do that because these are the sides that are going to be proportional. They're going to make that fraction that's going to be the same each time. So if you imagine, just like we did on the first slide, we could set them up as they will always equal the exact same fraction every single time when reduced. So I'm just going to go ahead and pretend that the sides are A and B. Since it's going to make the same fraction anyway, I'm just going to put these in there. So XZ, it's going to be A. It's the top part there. XY is going to be A. XZ on the bottom is going to be B. So I'm going to plug those in. First of all, I've got XY is A. So XY is this right here, XY. That's A. Okay, so XY is A, and we know that XZ is B. So we're going to put that in there just to try these out. XZ is over here. That's this whole line over here. That one's B. Now, I could do YQ and ZP. I'm going to look at XQ. I'm going to look at these right over here, XQ and XP. So XQ is A. So XQ is A. I'm just reading this off of what we just set up there. And XP is B. That's this one right here. Again, I said this is going to be one of the complicated ones. So I know that. Well, if you look, it kind of looks like side angle side I've got set up there, because the ones that we're trying to prove are similar are XPQ, this one right here, and XZY, this one right here. So if these are similar, then maybe I could use side angle side to prove it. I already see that they have a congruent angle in the middle. So I need to check whether XP over XZ, XP over XZ will be equal to XQ over XY. That's the two sides that we've kind of got set up there. So I'm going to just plug in what we've already got and see whether these are in fact the same thing. XP, if I look at my triangles there, XP is B, and XZ, well, that's also B. It's right over here. B over B is equal to XQ, let me see, XQ is A. I'm looking at my chart over there. XQ is A, and XY is also A. So what I've got is a statement that says B over B is equal to A over A. And my question is, are they the same thing? Well, remember, anything over itself in a fraction will equal 1. So B over B is going to be equal to 1. A over A is going to be equal to 1. These are definitely the same fraction. So what we've got is, yes, those are definitely proportional, but we had to use all those proportions from the first set of triangles to get us through the second set. So I realize that's a tough one there, but it helps us understand all the relationships that are going on with triangles. All right, last slide. It says, name the similar triangles and give the postulate or theorem that justifies your answer. So I'm looking at this first one here, and whenever you have a triangle within another triangle, you're going to have an overlapping angle right there. So that's a good thing to look for. I shouldn't say always. There will be situations where you won't have them. There's going to be some complicated things in the future. But if you look at the big triangle, it says, name the similar triangle. So we have to name them. So we have that little triangle on top up here that has its top angle, and the big angle here that has that same top angle there. So what we've got is angle, angle. We definitely have that. There are two angles. 80 is in one triangle, 80 is in another triangle, and that top angle, whatever it is the same. So when I do my triangle similarity statement, it's going to say triangle something is similar to triangle something. Now, I don't care what you pick for the first three letters, but whatever you pick, it's got to be the same exact pattern. So I'm going to start up here at this like single lined angle and go down to 80 and over, ADE. So I'm going to go ADE, and then I'm going to do the same thing on the big one. A down to 80 and over to the one that I don't know, which would be ABC. So I have my similarity statement, and I know why they are congruent. Why they are similar. This second one, we may have a similar statement, similar setup here. I see that there's a triangle within a triangle. There's a small triangle here, and then the large triangle. They're each going to have this angle up top, but then they have given me a whole bunch of side information. My guess is that I might be able to do side angle side again, because we have an included angle in between these sides, and that's what we're looking at there. So we definitely have that congruent angle up top. That's there. That's something. So I need to check whether these sides are proportional. So if you look at the left-hand side of the small triangle, its length is 6. And if you look at the left-hand side of the big triangle, its side length is 6 plus 3, or 6 over 9. And now I'm going to do the same thing with the right-hand side. The small right-hand side is 10, and the big right-hand side is 10 plus 5. Or 10 over 15. Now I need to see whether these are the same fraction. So 3 goes into 6 twice, 3 goes into 9 3 times, 5 goes into 10 twice, 5 goes into 15 3 times, 2/3. We've got an SAS situation here where these are similar by SAS. Our last one here, we have two triangles. Now, I don't know whether these are drawn proportionally or not. Maybe they are, maybe they're not. So we have to kind of take a look at them. So even if they don't look alike, these diagrams may not be to scale, so we always have to kind of assume that. Well, I don't see any angle information, but I do see side information, so the best I'm probably going to be able to do is side, side, side. But the hardest thing is which sides match up to which sides. So notice that little triangle up top. It's got a small side, a medium side, and a large side. Whereas the big triangle has a small side, a medium side, and a large side. And I know this one is large because it's 6 plus 6, that's 12, that's the largest side. So I'm going to check whether they are proportional by matching the small side with the small side, then the medium side with the medium side, and then finally the large side with the large side. So 3/6 reduces to 1/2. 5/12 does not reduce, it stays as 5/12, and 6/12 reduces to 1/2. So these, in fact, they are not similar. They are not similar triangles because we do not have this equaling 1/2. If that had been 6/12, then we'd say, okay, these are similar triangles. They're not. So if this 5 up here had actually been a 6, we would be okay. But since it's not, we can say that these two triangles are not similar.